I'm Richard Taylor, CTO of Vector Photonics, and today I'm going to talk about our pixel technology, which is the first breakthrough in semiconductor lasers in 30 years. I'll discuss the history of semiconductor lasers, explain how photonic crystal surface emitting lasers work, talk about how their advantages bring advantages for many markets. The evolution of the semiconductor laser. The first semiconductor laser was the Fabry-Perot laser. The way this worked was there were two mirrors, and light bounces back and forward between these two mirrors. This light is the feedback light. And from one of the mirrors, you allow some light to escape. That's the emission light, the standard laser light. This device, the feedback and the emission, are both in plane, both in the same direction and in the plane of the gain region. For a DFB laser, the mirrors are replaced with a grating structure. The grating does the same as the mirrors, but key to this design is that the feedback and the emission are still both in plane, the same as the Fabry-Perot laser. The next major breakthrough in semiconductor lasers was the vertical cavity surface emitting laser, or VCSEL. And the idea behind this one was to rotate everything to create a surface emitting laser. So in this case, two gratings above and below the active create feedback out of plane. Then one of the mirrors allows light to come out, which is the emission, and that is also out of plane, creating a surface emitting laser. The advantage of a surface emitting laser is that test and packaging are much cheaper. But crucially for a VCSEL, the speed, which is data rate, is also much higher than for an edge emitting laser. However, the power is much lower than an edge emitting laser. The photonic crystal surface emitting laser, or PCSEL, is the latest breakthrough in semiconductor lasers. This is the only laser where feedback and emission are in different planes. So in this device, a 2D grating creates two-dimensional feedback in plane and also creates out-of-plane emission. Now what this means is that you get all the advantages of a surface emitting laser, cheaper testing, cheaper packaging, higher data rate, but because you still use in-plane feedback, you get all the power advantages of an edge emitting laser. So why would you want to make a PCSEL? If you're picking a semiconductor laser, you can choose between power, speed, and cost. Basically, you have to pick 2 from 3. PCSEL is the only laser technology to optimize power, speed, and cost simultaneously. In addition to this, you can have high coherent power, phase control, which leads to beam steering, high speed, and low cost, all from a single device platform. Coherent arrays. I mentioned that the photonic crystal laser has in-plane feedback and that it's two-dimensional. And this property allowed us to invent the coherently coupled array. We created a 2x2 array of pixels, as depicted here, where each of these circles is a photonic crystal surface emitting laser. The light comes out the top. We took 2 of these devices and overlaid their light onto a camera. You can just see a lasering spot. There's nothing particularly exciting there. However, between the 2 lasers, we place a coupler region. Now, because we have a coupler here, what we can do is apply current, and that makes the region transparent. So the in-plane light can be coupled between 2 elements. So we can effectively make the 2 devices link up. And that's what is shown in this middle image. By applying sufficient current to the coupler region, we can make it transparent and create an interference pattern, which proves the 2 devices are coherent. The next thing we did is we separated 2 devices diagonally to prove that we could do this in 2 dimensions. So these devices are separated diagonally in a 2x2 array. We make the regions between them transparent, and we can still get the interference pattern, which proves coherence. Now, coherence is important because coherent light can be focused down to a much smaller spot than incoherent light. What that means, you can get more power per unit area. This has advantages in cutting, welding, melting, engraving, drying applications. Because of the way our devices are made, you can create an n by n array, which allows unlimited power scaling. leading to high brightness. And our unique geometry enables kilowatts of coherent laser power, something which isn't achievable with any other laser type. Beam steering. Once we've got an array structure and we can control the coupler region, what we can do is create what's called an optical phased array. So by tuning the phase of each of these two elements through this coupler, we can electronically steer a beam. So instead of the laser light coming straight at the top, we can steer the angle of emission electronically in real time. This is how current radar systems work. And this system has applications in LiDAR, whereby you can steer a laser beam to do imaging. Because we can do it electronically, we remove the need for mirrors and moving parts, which reduces the system size by about 10 times. And on the right here is a series of arrays that we've got under test. High data rates. If you compare pixels to other laser types, for the same size, they are more than 2.5 times faster than the next fastest device. And that's based on resonant frequency, which is how quickly a device can be turned on and off, effectively how high the data rate can get. So pixels are at least 2.5 times the next closest competitor. This unique technology supports higher data rates than conventional lasers. Wavelength flexibility. There are a number of materials with which you can make your laser out of. Each material emits light in a certain color, and for physics and engineering people, color is wavelength. So if you want to emit at a certain wavelength, you have to make your laser with a certain material. Other laser systems can only be made in certain materials. So VCSELs, for example, are extremely challenging to make in indium phosphide, which means you can't make the right color laser for communications applications. The photonic crystal surface emitting laser is material agnostic, which means it's wavelength agnostic. We can make them in any material, so we can make any wavelength the customer requires. And we still get all of the other advantages we've spoken about here. Papers and patents. We've published a number of papers on photonic crystal surface emitting lasers and have 2 granted patents. 2 patents are granted in the European Union, one of them is granted in the US, and we're looking to extend the regions of both of them. In addition to this, we're looking to file at least 2 patents per quarter for at least the next year. Thank you very much.